We just saw how to grow a regression tree, and now we'll talk about growing a classification tree. Growing a classification tree. So we'll see that we follow a very similar greedy procedure as for the regression case. So we've got some, our abstract space RD here, and all of our points in the classification case, they have all got labels. So maybe we've got some points, some red dots, and maybe we've got some blue, I don't know, maybe make them X's, we got some blue X's. And a little bit of notation to make our lives easier. Let's say if we got some arbitrary subset of RD, called R, so we have some subset R, then we'll define E sub R to be the fraction of, so we're going to count the number of points of each class in R, and if we wanted to assign a label to this region R, we would take a majority vote. So in this case we've got 4 blues and only 4 blue X's and 2 red dots, so we would classify a new point in this region, say this one, as a blue X. So it's the fraction of points xi in our data set. Remember, we have some data set as usual, x1 up to y1 up to xn yn. So it's the fraction of points xi in our training data set that would be misclassified, points xi in the region R, that would be misclassified by a majority vote in the region R. So in this case, how many would we get wrong? We're classifying them as blue X's and there's 2 reds, so we would get 2 out of 6 wrong. So that would be 1/3 wrong for this R here. And we could make this a little more formal if we said this is the, so if nr is the number of points in R, this would be the, we would kind of, to make this look similar to the regression case, so we would take the min over all the possible classes y of the fraction of points, and that can be written as, I'll say what nr is in a second, the number of points, which we can write using this indicator function, that are not equal to y. So this tells us the number of points in R for which the label is not equal to y, and nr we'll say is the total number of points. So that's just, well, nr is just, well, I can just write it as the number of i's such that xi is in R. Total number of points in our training set that is in R. So this is exactly what this is, by taking a majority vote. And now we've got this nice little notation. We can very easily define our procedure for growing a tree, a classification tree. So I'm drawing in higher, give us one more dimension to visualize. This is our RD. It's got more than 3 dimensions in general, but we'll just think about, since we can only draw 3. And what we will do is, for the first split, so we're growing this binary tree, and for the first split in the tree, we will choose j, a dimension j, and a split s to minimize. So I'll need a little bit notation here, I guess. So I'm going to minimize ERJS plus ER prime JS, where, so a little more notation here. So if J is 1 and S is this point, then we might make a split here. And let me call RJS. So we'll call RJS the points. This is the set of all the points xi in our data set, such that xij is greater than s, and we'll call r prime js the other side. So xij is lesser or equal to s. So this would be r js, and this would be r prime js, if we took j equal to 1 and s equal to this point. So we're going to choose the split that minimizes this quantity using this definition here for the error. So this is like the error on the r prime region, and this is the error on the r region. And now for the general case, we've got, so we have our first split in the tree, and let me associate a region. Let's associate a region with each node in the tree. So the first region we'll call R1, and that'll just be the whole space. And then we'll number these nodes. Maybe this is node 1, node 2, node 3. Every node in the tree will give a number, and we will associate a region with that node. So that would be R2, this would be R3, and so on. And R2, so let's call this R1, since this was our first split. This is R1, and this is R1 prime JS. And so R2 will be, for the J and S that minimized this, it will be R1 JS, and R3 is going to be R1 prime JS for the J and S that minimized this on the first split. So we're just dividing this up, and we're assigning one of these regions to this next node down, and we're assigning the other region to this other node. And now for the in general, so we need to define how we're going to split at a general node. So in general, we'll be at some RK. Maybe it's one of these, but in general, some RK. And so we need to split RK. So splitting RK. To do that, we choose, just like before, choose J and S to minimize ERK JS plus ER prime K JS. So if K was 2, for example, then here we had, this was R1 prime, then this would also be R2, this right hand side, and R2JS, if J was 2, say, and S was this quantity, we're going to split R2 at this S, and we're splitting along this plane, and RK JS, just like before here. I'm going to define it. Well, let me just modify our previous definition. We can just generalize this to RK, and this time it's only going to be the points in RK. So this does indeed generalize the previous definition, because when it was R1, we were considering all the points xi in our data set. So these are also points in the data set that also lie in RK. And the first case, our RK was 1, so it was all of RD. So this agrees with our earlier definition. So that should make it, maybe to be precise, these are not all points in RK, but these are points in RK that are in the data set. So at the general step, we need to split RK. We're here and we look over all dimensions, we look over all split points, and we choose the plane that minimizes this quantity, where RK would be like this region here, and RK prime might be this other region. And we're minimizing the sum of the misclassification error that would arise by classifying the points in each of those two regions according to a majority vote in that region. This gives us a procedure for building this tree. So we get this infinite tree if we were to just continue doing this forever, but we'll use a stopping criterion just like before in the regression case. So our preferred or a better stopping criteria, then we could stop if there's only one point, but another option would be stopping when or only considering splits when the resulting regions would result in some minimum number of points, say 5. Or in the classification case, another option, option C, would be to stop so we would stop at RK when RK contains points only of one class. So this would be another possible stopping criterion. So this defines a procedure for building a classification tree, and it can be generalized, so we use the misclassification error here, but this can be generalized to use other types of quantities to minimize, such as, so one would be the entropy. I haven't defined entropy, but another possibility which people often use and some may give better performance is to use the entropy, or another possibility is to use what's called the Gini index.